We have all tried to fix a broken device and hit a wall. Usually, it's a literal wall of glue or a strange proprietary screw refusing to budge. When regulators look at this problem, they see the exact same thing. From the EU's eco-design regulations to the Repair Association, the global legal consensus zeroes in on the connection points holding a device together. The legislation explicitly targets industrial adhesives, proprietary screw vids that require special orders, and software that pairs individual parts to serial numbers. Regulators focus on the joint because a joint is a physical thing. You can hold a screw, inspect an adhesive seal, and write a clear law mandating that commercially available tools must be able to break them. Because of this focus, the entire public and legal push for the right to repair revolves around what kind of fastener is used to seal the box. But if we take two theoretical smartphones, we can use standard screws, identical glue, and basic tools on both, and end up with completely different results. This schematic compares the internal layers of two phone designs. Phone A has its battery sitting right underneath the outer back cover. Phone B buries its battery under the display, beneath a structural bracket and underneath the mainboard. For Phone A, swapping that battery is a 5-minute job. For Phone B, the internal layout creates a repair job so complex that no shop will quote you a sensible price to attempt it. The arrangement of parts, an invisible structural choice, governs repairability long before a tool touches a screw. What actually dictates repairability is the depth of the component chain. It is the specific sequence of parts you have to remove before you finally reach the broken one. To map this, we look at what engineers call a dependency graph, a diagram showing what must be removed to reach a specific part. Here we have two data trees. The left tree shows a flat topology with 40 nodes directly connected to the top layer. The right tree shows only 6 nodes, but they are stacked sequentially in a deep chain. Every time you step deeper into a dependency graph to reach the next layer, you introduce a new chance to snap a ribbon cable, strip a screw head, or tear a water seal. The math of repair is unforgiving. Removing 40 accessible screws in a flat one-layer layout is always faster and safer than carefully extracting just 6 screws in a deep, layered structure. That sequence of removal is a spatial relationship between components. Because order is not a physical component, it remains completely invisible on a product's bill of materials. This creates a dilemma for lawmakers. It is relatively easy to ban a type of glue, but incredibly difficult to write a legal rule governing an invisible sequence of parts. To address this, the law is moving upstream. Regulators are slowly shifting away from measuring the finished product on a desk and are attempting to constrain the spatial partitioning decisions made during early design. Take a modern laptop keyboard. Designers often draw the boundary of a replaceable unit around an entire soldered top case. If one single key breaks, you have to replace the whole housing. No amount of universally standard, easily removable screws can salvage a bad partitioning decision. A meaningful repairability law has to force a change in the architectural layout itself. Device maintenance is simply the factory assembly process run in reverse. The exact sequence of that process is permanently locked in place the moment a design team finalizes their initial layout. Placing a battery above a motherboard instead of trapping it underneath is a painless choice if made early. Once the design moves forward, it becomes structurally impossible to reverse. Repairability is not a feature you add at the end of a development cycle. It is a shape drawn at the very beginning. There is a stark contrast between the freedom of a concept and the rigid permanence of the manufacturing floor. During the sketch phase, moving a component from the bottom to the top costs nothing. After physical tooling has begun, changing that exact same component requires an entirely new manufacturing program. Design choices are as cheap as a sketch as an idea, but brutal and unforgiving once stamped into metal. Simulating these architectures during the generative phase allows teams to identify structural traps before committing to hardware. This focus on consistency and early-stage spatial intelligence is the core mandate of Depix. Sustainability is a property of the initial sketch, decided at the designer's desk long before the product reaches the repair bench.